Okay, today we're going to discuss an important class of schemes or important class of phenomenon that we need to add to our differential equations in atmospheric science very often. And those are oscillation and decay equations. And this is a little bit underappreciated type of phenomenon in terms of numerical representation in our models. I think we all tend to concentrate very much, of course, in advection and diffusion processes, not so much into these guys, but they are everywhere in our equations, and very often I see in the numerical codes in models how people pretty carelessly, for example, add so-called decay equations, which are, for example, lots of those equations in microphysics. So let's consider first type of phenomenon, oscillation. And oscillations in meteorology are caused by such things as, for example, Coriolis force. So you will know from your dynamics class that Coriolis force causes so-called, by itself, without pressure gradient. So it's not like quasi-geostrophic or geostrophic phenomenon I'm talking about here. This one is just oscillations caused by Coriolis force or rotation of Earth. So that's called inertial oscillations. And for inertial oscillations, let's consider two equations for horizontal velocity components. So the first one, du dt equals to fv, where f is Coriolis parameter, and you know how what it's equal to 2 pi angular frequency, so it's 2 pi divided by a period of 1 day in seconds, times sinus latitude. So it's zero. Coriolis force is of course zero at the equator, and it's a maximum at the pole. So this is a component for zonal velocity, and for meridional velocity you have dv dt equals to minus fu. So this is normal terms that appear in our dynamics equations together with some other terms, but these terms just consider here by themselves, and we need to be very careful with those terms. So it's just an example of oscillations that can be caused by Coriolis force here. So to solve these equations analytically, usually what is done is we consider complex numbers, because that's the easiest way to solve this. So we consider some complex plane velocity equals to u plus iv. So and then where I is just imaginary unity, square root of I of 1 of minus 1. So if you do that, it's easy to show that these two equations degenerate into one equation, du dt equals to minus I Coriolis force u. And of course solution of that, it's very easy, because if you assume that f is constant, it does not change with time, so for a specific place we get solution that u equals to e to the power of minus I f t. So written as cosine sine, it's cosine f t minus I sine f t. So you see that so u equals to cosine of t, using this definition, and v equals to minus sine of t. Of course, some u naught here. So it's u0, v0. At some velocity at some initial moment. So definitely, so what's this what this equation describes is just basically rotation of velocity vector. So on Earth surface, what inertial oscillation looks like is this kind of air is moving in circles with different radius depending on how close or far away from the pole. In order to include this in these Coriolis terms, when we include Coriolis terms in our dynamic equations, we need to choose then a certain time scheme that we usually choose not just to include this Coriolis terms, but to solve for our advection, for our diffusion. So the choice of time scheme is usually dictated by those. And then we need to be careful because those terms with a given time scheme can be actually unstable. So let's consider several possible schemes for oscillation equation. So from that example that I gave you, we see that the general form can be like we are looking at some function d phi dt equals to I omega phi, where omega is some frequency, 2 pi over f, well, where f is not Coriolis, just frequency. So omega is just angular frequency. So this is general form where I is the imaginary unity. So let's consider several schemes for that. So example 1, let's consider Euler scheme. So we have f phi n plus 1 minus phi n divided by delta t equals to I omega phi n. So Euler scheme, we have this forward in time scheme, approximation, forward in time approximation for time derivative, and right hand side is evaluated at time level n. So now if we write it as a one equation, we have phi n plus 1 equals to phi n 1 plus I omega delta t. So this is basically, in a way, it's an amplification factor, lambda. So you see it's changes amplitude on time step n to get amplitude at step n plus 1. And so obviously from this, you can see that lambda, absolute value, is greater than 1 for any delta t. Well, we just looking at imaginary plane. So we see that this is 1, so it's here, and I omega t, so it's omega t with, so this is basically this guy. So it's shifted circle, and depending on angle, for some harmonics, for some delta t's, it's so to show that, just make lambda square equals to real part squared 1 plus omega squared delta t square. So we see that this obviously is greater than 1. So this scheme, Euler scheme, is unstable. Unstable. We can't use it for any delta t. So Euler scheme we cannot use. All right. So let's consider example number 2. Implicit scheme. So we have phi n plus 1 minus phi n divided by delta t, so forward in time. But right hand side will be evaluated at time step n plus 1. So here we don't have to solve any matrix or anything. We can directly evaluate phi n plus 1. And so if we can rewrite this equation as the following: phi n divided by 1 minus I omega delta t. So let's write it at get rid of complex number from the denominator. So we multiply by conjugate. In that case it's 1 plus omega square delta t square. Here we have 1 plus I omega delta t times phi n. So this is simplification factor. So this simplification factor, amplitude of it, equals 2, 1 divided by 1 plus omega square delta t square, and here is 1 plus omega square delta t square squared. So this is, we find square of amplitude. So we divide by 1 and get 1 plus omega square delta t squared and square root of it. So, and it's obviously for any delta t, the thing is smaller or equal than 1. So it's always stable. Stable for any delta t. So implicit scheme is a scheme to use for oscillation equations. Unfortunately, of course, we cannot use. Actually, even this, if we use implicit term here and other terms are explicit, like some advection term, diffusion term, we can still use implicit here. So we just will move to the right hand side, and the whole equation will be divided by this guy. And so we can actually use implicit scheme even if we have other schemes, other terms here like advection and others as an explicit scheme. Okay, so so in principle, Coriolis terms can be used as in implicit form. Okay, let's consider another example. Another example, leapfrog scheme, our favorite one to make fun of. Phi n plus 1 minus phi n minus 1 divided by delta t equals to I omega phi n. So don't forget, we kind of consider it as this kind of separate equation, but in reality, when we use leapfrog, we have some other terms here, diffusion, advection, and so on. But because it's linear scheme, so stability of this scheme only will dictate stability, like will be combined with stability with other terms. So that's actually an important point when you consider linear stability due to advection, diffusion, and in this case oscillation. Your delta t should be smallest of all three criteria that you would get, like for separate for advection, separate for diffusion, and separate for, say, oscillation, in this case, or Coriolis force. The smallest delta t you will get is dictated by the time step will be dictated by the smallest allowed time step for each of those processes. So so in this case, for leapfrog scheme, if we solve it, and in this case we use amplification factor again, that defined as the following: some lambda times, so times step n plus 1. So if we substitute it and the same way, so it's equals to lambda phi n squared n minus 1. So if we substitute all this in this equation, we'll derive that lambda equals to I omega delta t. In this case, because we have three time levels, we have a quadratic equation for lambda, as before we had for leapfrog scheme, and so we have two solutions for lambda. So it's I omega delta t plus minus square root of 1 minus omega square delta t squared. So in order for, so we need this guy to be smaller than 1, so that it would be positive. And that in that case, so omega square delta t square smaller than 1. In that case, lambda will be actually squared equals to 1, which means that amplitude of lambda will be 1. So in that, if you use this scheme, for this condition, this leapfrog scheme would produce no decay in amplitude. So that would be basically the exact solution in a way for that, because exact solution does not change amplitude, it just rotates it. Say amplitude of a vector of velocity or wind, it will just rotate it without changing amplitude. Coriolis force doesn't change amplitude of wind, it just rotates it, like turns it. And so you see that, but condition is this, that delta t should be smaller or equal than 1 over omega. Which means for Coriolis force, we have omega which is equal just Coriolis parameter. Coriolis. Delta t should be smaller or equal than 1 over f. So f generally in mid-latitudes, so in mid-latitudes you have f in the order of approximately 10 to the minus 4 inverse seconds. So delta t would be smaller than about 10 to the power of 4 seconds, which is plenty. It's 10,000 seconds, so about 3 hours. So there is no problem usually with Coriolis force if you use leapfrog scheme, because your other processes will dictate much smaller time steps than this one. But nice to know that leapfrog scheme would not change amplitude. Okay, So so usually Coriolis force combined with other schemes like advection, explicit schemes, written as an explicit scheme, does not cause any problem for stability, because stability is dictated by those advection and diffusion processes, not by oscillation due to Coriolis force, because the time scale of those oscillations is very large compared to time scale of diffusion or advection. Okay, but let's consider another process, which is decay. So decay process, usually we use it for nudging things, or what's nudging. If we, for example, specify, we have a simulation, and then, but it produces some errors, right? And relative to observations, and we, for example, study, say, some process, a small scale process that is not resolved by large scale model, and we say use output from large scale model, say forecast model that with grid spacing of say 20 kilometers, to drive our small scale model that resolves clouds with like grid spacing of several hundred meters, let's say. But we don't. We want to impose this large scale flow. So what we do usually, we put to the right hand side some nudging terms that would basically steer our large scale solution towards that kind of our small scale solution toward large scale solution over some time scale. So basically, like for example, if we want to nudge, say we have equation for horizontal velocity, we have some bunch of terms here, and then we wanted to nudge to some prescribed flow. Then we add the terms like the following: u minus u large scale divided by some tau. So let's see, if u is greater than this large scale, then divided by tau, so this term will add to u. We need to so if it's greater than u, it will drive it even more away. So we need to put minus sign in here. So in that case, you see when u is greater than what you prescribe, then with minus it will reduce u. And if u is actually smaller, then this becomes negative. Positive, it will start accelerating it. So basically this term will nudge over time scale tau the solution towards this your prescribed velocity. Another application for that, if we want to get rid of some waves high in stratosphere, for example, in stratosphere where outside domain top is like at the height of say 30 kilometers, and convection below in troposphere generates these gravity waves that propagate into the stratosphere, and because density in stratosphere very quickly falls with height, eventually they may collapse, for example, and generate all sort of noise, or they just can propagate upward, and then usually at the top we put some lid as our boundary condition, so we put some solid kind of wall there. And if not dealt with, these waves would strike the ceiling and then reflect back, and we would not want that. So we need to get rid of those waves at certain heights, so we put so-called damping layer, say 10 kilometers deep in the stratosphere, where we damp, say, horizontal or vertical velocity to 0. So basically this prescribed thing becomes, so our term becomes something like that. Say it's vertical velocity w dt, some terms here, and here we have w divided by tau, where tau can be a function of height. So this kind of tau gradually decreases with height, so that our damping scale, time scale, becomes smaller and smaller as we get toward the top boundary condition, and that thing would damp our gravity waves that propagating towards our lid at the top, and that would deal with this problem and mitigate this kind of problem of reflected gravity waves from the domain top. So there are lots of equations like there are lots of terms like that in our model. So we need to, let's consider what times do those terms affect time stability and impose some limitation on time step. So let's consider so decay equation. So generally it's written like minus, say, phi divided by tau. And phi minus 5, 0, some value, it does not affect it because we can just redefine variable so that it would look exactly like this. Even if we have like u minus u prescribed, we just define new variable phi equals to u minus u prescribed, and then we have this form. So this is general form of decay equation. So how we solve it? Let's try different examples. So example 1, Euler equation. So we like Euler even though it never works. Phi n plus 1 minus phi n divided by delta t. And right hand side is going to be phi n divided by tau. So let's write it as one equation. As just explicit with respect to n plus 1. We have phi n plus 1 equals to phi n times 1 minus delta t divided by tau. So first of all, so this is simplification factor, and of course we want our amplitude to go down. This is the whole point of this decay equation. So amplitude should reduce, and we see that so this amplitude indeed becomes smaller than is smaller than 1, but at certain value delta t, it can actually start, if delta t is greater than tau, you see it may start create negative solution. So it multiply by negative number, and then at next time step it becomes again, it's also negative, it becomes positive. So it starts kind of jumping from positive to negative, positive to less. This is not good. So it's not definitely decay. So in order for the scheme to be decay equation, we need delta t smaller than 1 than tau. So this is our criteria. So when our time step smaller than tau, the Euler scheme can actually be used, and it behaves like normal, like indeed like decay equation. On each time step, amplitude would reduce. Okay, that's nice. Let's consider another example, implicit scheme. So you see that for Euler we can use it. It's not unstable, but there is a stability criterion. Delta t cannot be smaller than cannot be larger than our decay time step. And why it's decay? Because well, I didn't mention it, because solution of this equation analytical is phi equals to some initial phi e to the power minus t divided by tau. So you see that as time progressing, it decays by a factor of e over time tau. So this is why it's decay. So many problems like that, for example, nuclear decay or some other decay is described by this equation. So in order to solve it, if for example your tau is not constant or something, then you may not solve it analytically. So in this case you need numerical solution, but analytically it's also very easy to solve. So, but let's consider implicit scheme. Implicit scheme. So we have phi n plus 1 minus phi n divided by delta t equals to minus phi n plus 1 divided by tau. So you see right hand side is evaluated at n plus 1 time step, so it's implicit. And let's write it like the following. Phi n plus 1 in that case equals to phi n divided by 1 plus delta t divided by tau. So we see that this guy is always positive and greater than 1. So 1 divided by number which is greater than 1, always smaller than 1. So we see that in that case it's always decaying. So amplitude would, and each time step would decrease regardless of time step you use. You can use very high large time step. If this time step, let's say 10 times bigger than tau, you will immediately in one time step will go to 0, which is should, according to this equation, eventually it goes to a very small number. Of course, it may not be very accurate because what's going on here is time is going this way, and this is your phi, and this is your initial phi. Then according to this equation, it should decay like that. So basically, by this equation, what we do, we replace it by just some line. Okay, so but it's stable. So delta t can be any delta t. So stable with any delta t. So as usual, we see this nice property of implicit schemes. They're usually completely stable for any delta t, but sometimes they can be hard to solve, but in this case there is no problem. We can safely use an implicit scheme. It's a very simple one. You don't need to invert any matrix or anything like that. Okay, so it's stable. Example 3. So now let's say that you use a leapfrog scheme. Because very often when you use leapfrog scheme with your advection, with your diffusion and other processes, you just add this damping or decay term to your right hand side of your momentum equations or your some other equations, like some equation for scalars and so on, for temperature, for example. So you just add it to the right hand side, and then you evaluate it according to leapfrog scheme on time step n. So let's use leapfrog. So delta t equals to minus phi n divided by tau. So now your right hand side is estimated at, of course it's 2 delta t. It's estimated on time step n. So now if you solve this equation, and you may find out that, well, if you use it like this, you have 2 amplification factors, and again, as we did before, you define amplification factor as the following. So that phi n equals to lambda phi n minus 1. So you substitute in there, then you will have equation, quadratic equation for lambda from this equation. And if you solve it, then you will find that lambda equals to delta t divided by tau plus minus 1 plus delta t divided by tau. So this real solution, there is no imaginary part. So from that you see that there are 2 lambdas, and one of those lambdas is, and they both coexist at the same time, so there is computational mode here, right, as before. The real mode, though, is always greater than 1. So for this plus sign here, we see that this guy is greater than 1. So that mode will make it unstable and will blow it up. Leapfrog scheme is unstable. Unstable for decay equation. Decay nudging terms at time step n for leapfrog. So can't use it. So, but what to do? If you need, you use leapfrog scheme, you need to use your decay. Well, it's actually what you need to do, similar to diffusion. Remember that for leapfrog scheme, diffusion part of that equation cannot be evaluated at time step n. It should be put at time step n minus 1. And diffusion, in a way, it's also like decay equation, right? So in this case, it can be actually shown that if you put your right-hand side of this decay thing, this is what you should do. You should put it at n minus 1. In this case, there is only one solution. There is no computational mode actually, because you have only two time steps here, time level, n plus 1 and n minus 1. You skip time step n for this decay portion of your equations. So then you have only one, you have solution for lambda. Lambda square equals to 1 minus 2 delta t divided by tau. So you see that lambda squared is smaller than 1. Okay, but it should be real. So as long as this guy, the whole thing is actually greater than 0. If it becomes smaller than 0, then it becomes a complex solution. So it's oscillation, it's not actually decay. It will produce oscillations. So basically we conclude that stability criterion, or not even stability in this case, it's not going to blow up, but to serve its purpose as a decay equation, for this, in this case, your delta t should be smaller than 1/2 of tau. So this is criterion. And you need to implement it for leapfrog scheme computed on time step level n minus 1. So this is your criterion. So as long as you keep this, it will be okay to use decay to use this form of decay equation using leapfrog scheme. Okay, so you have to always be careful. Like for example, if you use Adams-Bashforth criterion, then actually you can find that this delta t should be something like 1/3 of tau. If you use Adams-Bashforth third order, for example, scheme, so it's more restrictive unit than this one. So it depends on scheme you use. Okay, so next one, let's consider so-called nonlinear decay or nonlinear conversion terms that very often appear in microphysical parameterizations. So when you, for example, compute conversions of cloud water into rain, or some accretion processes when you rainwater falls through cloud water and collects it and grow. There are all sorts of these equations that generally have the following form: that some of your quantity phi, say cloud water content due to some process, or rainwater or ice water or snow, generally may look like the following. It's some minus alpha phi in some power beta. So it's basically decaying phi collected, say this is cloud water collected by rain, and this process is actually proportional to cloud water itself with minus sign, and it's some power beta, which can be some, I don't know, some crazy number. So very often what I see in numerical codes, even in pretty established models, people just use kind of time splitting and basically subcycle this process as the following, using, say, a simple Euler scheme. This n in the power of beta. So they just write that phi n plus 1 equals to phi n times 1 minus alpha phi n, the power of beta minus 1. So this is basically how times delta t. And of course, if you, depending on your value of alpha or your phi n, this guy may become negative, and phi, if it's cloud water, of course, cannot be negative. So what people do, they put if statement there, like if this guy is negative, it's equal to 0, kind of nonsense like that. I see it all the time in codes. It's basically just this kind of fixers. So people just use this explicit scheme, like earlier type of scheme, for this kind of microphysical process, and then just use if statements to fix them afterwards. And this creates huge mess, actually, in the code. And also, you can fix it, but some of that went to rainwater anyway, so then you need to fix the mass, so to make sure that the amount of cloud water that went to rain is actually the same amount that rain actually gained, so that the total mass is conserved. So all sorts of issues. Instead of just Euler scheme, don't use it. Never use it for microphysics. And you see this, at some phi it can be actually stable or produce positive and normal values. But then if phi, for example, is large enough for given alpha or beta, it's all of a sudden becomes negative. So it's completely unpredictable behavior here. And it's not only one process there, it can be dozens of processes like that. And it creates tremendous mess. And it's difficult to program if you consider one process at a time. So what else? What you can do instead? Always use implicit scheme for processes like that. So how you do it? Well, first of all, you linearize it. So you basically use the following scheme: phi n plus 1 minus phi n divided by delta t equals to alpha. And if we use n plus 1, it becomes pretty difficult equation to solve. So it becomes nonlinear equation. Then you need to solve for n plus 1, phi n plus 1, using, say, Newton method or something like that. That becomes messy. So instead, and not computationally efficient. So instead, what you could do is just linearize it. You compute this phi power of beta and call it n at the time step n, and in the power of beta minus 1 times phi n plus 1. So you see, you linearize it around n, and so this is the form that you would use. And if you write it in a different way, you have phi n plus 1 equal to phi n well, just let's, yeah, phi n times 1 minus delta t, sorry, not that. It's phi n divided by 1 plus delta t alpha phi n the power of beta plus 1. So you see now, unlike this previous case, you have this guy, which is if phi n is positive, and this is for microphysics is always the case. It can be a cloud water content, or it can be concentration of some hydrometeor or so on, but they positively defined the positive quantity. So this guy is positive, and you take this phi and divide by some positive number. So there is no possibility that this guy becomes negative or like or even 0 completely. So you see that it's very safe, and moreover you can use it by combining various processes at once. So you have this some epsilon phi, some gamma, some other process and some other plus, for example, if it's gaining actually from some other guy, like depending on value of phi. So in that case, you also can show that the whole thing is basically well-posed problem. So so this is why kind of it's very important to use implicit scheme for in your microphysics. Yeah, so it's always stable, so always works. So implicit. So if you have this nonlinear term like that, always use implicit scheme. Linearize the implicit scheme, of course. Because if you use just then otherwise, if it's phi n plus 1 in power of beta, then this is nonlinear equation that you would need to solve using some Newton method, and that would be expensive. So it's better just to linearize it, and then you can just write it like that. Okay, doc. So that's all I wanted to say about this oscillation and decay equations.